This is a video of lessons learned of what I have learned from lectures of from David Silver on reinforcement learning. He published a playlist of videos on YouTube 7 8 years ago, um, which is quite famous in the reinforcement learning community because David Silver, who is also known as the creator of AlphaGo, he's also a research scientist at DeepMind. So I want to take this opportunity. I watched these videos 3 years ago. Recently, I was um, reviewing these lectures again, so I want to take the opportunity to record this video to record my uh, thoughts um, and and to illustrate my thoughts and explain my understandings of some of the ideas and algorithms he explained in the lectures. Hopefully, if you're also learning these lectures, hopefully this would also help. I think David really did a good job introducing the basic concepts and all the foundations, bricks of reinforcement learning throughout the 10A lectures, starting from lecture one. He explained what is reinforcement learning, and then he explained the structures of reinforcement learning, which is a Markov decision process. And then built on top of the Markov decision process, he explained dynamic programming, how using policy iteration and value iteration can solve the problem of reinforcement learning. So in this lecture, he used dynamic programming because the environment is on all the parameters of the environment is known to the agent, so you can use dynamic programming. But what if the environment is unknown? So in lecture 4, he introduced the idea of Monte Carlo learning and Monte Carlo evaluation and learning, and temporal difference learning, also known as TD learning. And then built on top of these concepts, he introduced on policy learning and off policy learning, which I'm going to explain in details in this lecture. And then starting from lecture 6, he expanded he basically scaled everything up. So all the lectures previously are using a matrix and tables, but what if the problem scales up, like solving AlphaGo? There are trillions of states that it is impossible to store everything in the matrix. So starting lecture 6, he started using functional approximations, which is in this case, he's using neural network to replace all the matrix and tables. So lecture 6 talks about uh, approximating the value functions using a neural network. And then lecture 6, he also replaced he used neural network to replace the action value functions, and talks about the idea of actor critic, which use both the value function and policy action state value function and policy action value functions. And then lecture 8, he combines all the previous ideas, and he introduced a model based learning. So all previous lectures was model free. I know nothing about the environment, but what if we build a world model that can predict everything? So instead of instead of creating a model of the agent, I can create a model of the world and use that to create the model of the agent. So that's basically what he is trying to explain here. And then the last two lectures, he talks about exploration and exploitation. I guess I'll skip the ideas for now, but I as I go through these lectures one by one, I think you would understand what these two terms mean. So without further ado, I'm gonna go through these lectures one by one, starting from lecture one. So reinforcement learning is part of machine learning. It is not a supervised learning. It is also not a unsupervised learning. With supervised learning, you have a training data. You have a labeled training data. You build a model using those data, and then you can predict. You can give an input and use that model to predict the output. And then unsupervised learning, you use a set of data to try to clustering them, separate them apart. And then reinforcement learning has no supervisor. The only thing that it has matters the most to reinforcement learning is a reward signal. Either you want to win a game, you want to reach to a terminal, reach to a goal in a maze, in the matrix. So reinforcement learning, defining the reward is the most important thing. And then the lecture explains several key concepts that he's going to use again and again these lectures. So again, reward. He defined the reward RT at time step t. It's a scalar feedback reward. It tells the agent how it's doing at time step t. Again, I think I forgot to mention one thing. The reinforcement learning, time really matters. It's sequential. It's like playing a game, playing a football game. Every time a player moves, the time is continuous. It's sequential. Each player has its own state, and the goal is to the goal is to shoot the ball into the goal. Every time, every state, each agent state matters. The action they take also matters. So that's the ideas here. Sequential decision making, which I just explained. The goal is to select actions to maximize the total future reward. Here he structured a model with an agent, how it interacts with the environment or the world model. At every time step t, the agent will take an action. Once he takes an action, he's gonna receive a reward, RT, from the model, the world model or the environment, and then he's also gonna receive an observation. Just imagine you're in a maze. Every time you decide to move left or right, you will receive an observation whether making left or right moves you to a better state, or receive a better reward. I mean, taking a left, maybe you see more possibilities of routes moving forward, so that probably means a better reward instead of taking a right turn. On the contrary, the environment, which is also a model, it will receive the action from the agent, and then at the next time t+1, it will emit the observation and a scalar reward. So this loop continues again and again and again until the agent reaches to the terminal or reach the final goal. So that's the structures AA used to structure the problem of using reinforcement learning. So several major components of a reinforcement learning agent. Either it may include one or more. A policy. A policy is an agent's behavioral function. Behavior function means what kind of action it's going to take. Like I explained earlier, either taking a left, moving forward, or taking a right turn. this is the agent's policy. It decides at this time step t and at the current state of the agent, the policy determines what is the next actions the agent is going to take. And then value function evaluates how good is each state and or action. So there are two kinds of value functions. One is a state value function. At current state, how good I am. So obviously, I just give you an example. 10 is better than minus 10. 5 is better than 0. So it's evaluating. It's a value function to evaluate how good I am at current state. And the other value function is called action value. It evaluates how good my current action is. Making a left turn is better, whether making a left turn is better than making a right turn. So there are two kinds of value functions. It's going to use throughout these whole lectures. Depending on the kind of learning algorithms, you can either use a state value based, or an action value based learning methods, or you can combine those, which is the actor-critic learning method I explained earlier. And then again, the last component is the model, is the agent representation of the environment. On the contrary, you can also build a model of the world, of the environment, which is covered in lecture 9. A lot of people nowadays talk about like world models. I think this is what it is. I think it is referring to this environment model, is using the environment model to predict the agent state. So again, a policy is the agent's behavior. It is a map from state to actions. A deterministic policy would be, I know exactly, at the current state, I know exactly what is my next actions would be. If I'm holding a piece of pizza, my next action is going to be deterministic because I'm going to eat it. And the other policy would be a stochastic. It's random. It has probabilities. I'm holding a pizza. Maybe 20% I'm going to eat it. Maybe another 20% I'm just going to put it down because it's not healthy. So it's going to be it's based on the current state. There's going to be a probability of each actions. That's called stochastic policy. Value function is a prediction of future reward. It used to evaluate the goodness, badness of states, and therefore to select between actions. So this is a state value functions. It should also has an action value function, but anyway, a state value function evaluates the current state. So R is a reward. It is the expectancies of the immediate reward plus the discounted future rewards given the current state. So if imagine I'm standing in a maze. If I take a left turn, I'm gonna move to the next state, or I'm gonna move to a next position in the maze. Whereas if I'm take a right turn, I'm gonna move to another position in the maze. So each of these positions will have a state value functions to evaluate how good that state is. And that state value function would be defined by, okay, once I take a left turn, what immediate reward I'm gonna get, plus all the discounted future rewards I'm gonna get. And once I calculate the state value function of either making a left turn or right turn, I can compare them. If, let's say, making a right turn, the position after taking a right turn, the state value function is higher than the value function of making a left turn, then I know that I'm going to make a right turn because I'm going to reach a better state. So that's what state value function means. The last component is model. A model predicts what the environment will do next. P predicts the next state. So R predicts the next immediate reward. So given the current state, given the current state at time step t, I'm going to take an action. What is the probability of reaching to the next state? So if we know this, if we know such probability, we would be able to predict. We would be able we would be able to know the environment. We would know the environment and be able to predict the next actions or states that I'm going to reach to. Similarly, if I know what kind of what reward I'm gonna get after taking an action, I would also be able to predict what the environment will do next, because I will be able to know the kind of the values of the reward that the environment will give to me. So that's a model. It's a it's a it's a you know everything. It's so rephrase it so better illustrate my thoughts. A model that the agent build to represent the environment, that model will tell the agent the probabilities of moving to the next state and the probabilities of getting the reward, and the probability of the reward after taking each action steps. Like I mentioned, there are two kinds of learnings: value-based, policy-based, and the combination of the two, which is actor-critic. With value-based, you only have a state value function. There's no policy, but you can implicitly infer the policy by comparing the state value function, like I just mentioned. You compare the state after making a left turn or right turn, and then it will tell you whether making a right turn is better than making a left turn. The policy is just using the action value functions directly to tell you which actions you're going to take. It's policy based. It will tell you directly. So making a left turn making a left has a action value function of, let's say, 5. Making a right turn has an action value function of 10. So obviously making a right turn is better because 10 is greater than 5. Actor-critic would be just combination of them, combination of the both. You use the I don't remember which guides which, but basically one of the I think policy will be guiding the value. The policy functions will be used to updating the value function. Two kinds of RL agents, model free. Everything before lecture 8, including lecture 8, is model free. I know nothing about the environment. I'm just going to be interacting with it. I will take whatever it gives me. But model based is I'm going to build a model of the world, of the environment first, and then use that to predict my next actions or states. So that's the difference here. Again, this chart illustrates the differences, the relationships of all these different learning methods. You have value-based on the left, policy-based on the right, and the intersection is an actor-critic. Model-free, and then model-based. Two fundamental problems in sequential decision-making reinforcement learning. It's the environment is initially unknown. The agent interacts with the environment. The agent improves its policy planning. Model of the environment is known. The agent performs computation with its model without an interagent improve its policy. So reinforcement learning is interacting with the environment. In the process of interacting with the environment, you gain better understanding of the with the environment. Thus, you improves the model of yourself. It's like learning soccer. At the beginning, you know nothing about the soccer, but as you practice along, you play with your friends, you improve your skills. You know what kind of actions you're gonna take if you know in a certain situation that you would know that whether you should shoot the ball or you should pass the ball. So that's reinforcement learning. Planning is okay. I already know about the environment. I need to know at this basically I'm the coach of my soccer team. Based on the current situation, the time freeze, I'm gonna plan how my player is gonna play the game. Okay, so player A, he should pass the ball to player B because I already know the environment. I know what the components is gonna do. The components is gonna come and try to try to get the ball. So I'm gonna pass the ball. So I'm gonna ask player A to pass the ball to player B, and then I know after passing the ball, the opponent gonna change their position. So I'm gonna ask the player B to directly shoot the ball. So this is called planning. This is like a coach coaching the game, coaching all these players. He is he is reasoning about the moves. He's introspecting, pondering about how he should plan the actions of the agent, the actions he's going to take, the states that he's going to move to. So that's called planning. It's also part of it's also very important part of reinforcement learning. And then lastly is exploration and exportation. Exploration is finding more information about the environment, like you're wandering in a maze. You want to know how big is the maze, um, how many closed or open walls it has. You're just wondering. You're not you're trying to figure out the environment. The more you explore, maybe there's a better chance to find a shorter or faster, better path to reach the terminal, to get out of the maze. So that's exploration. Exploitation, exploit known information to maximize reward. So if I know taking a left turn will always reach to the goal, so I'm at each step I'm always going to make a left turn. Obviously, if it is true, you're going to reach the goal. But what if you're only going to you're actually taking a bigger and longer path to get out of the maze? If you're only exploiting without exploration, you may miss information. You may miss a better path to get out of the maze. So it's usually important to both explore and exploit. So in the lecture, David, he dedicated one lecture to this concept. He had several algorithms to improve the exploration and exploitation strategy. Lastly, he explained the concepts of prediction and control. The prediction is basically given a policy, evaluate the future. It finds out the state value functions, and control is basically finding out the best actions it's going to take in order to optimize the future. So that's prediction and control. One is a state value function, the control is the action value function. So that's lecture one. He summarized all the basic ideas, key concepts of reinforcement learning, which he has lectures to explain details dedicated for each of the concepts. So with that, I'm going to move to lecture two, Markov decision process. This is the structures he used to structure the reinforcement learning problem. So first he defined a Markov state called ST state. A Markov state, it basically says with current state, it captures all the previous state. So I can just get rid of all the previous information as long as I know the current state. So that is called a Markov state. So this is a state. This is a PSS prime. This is called a state transition probability matrix. It defines, you know, if moving from state S to state S prime, from time step t to time step t plus 1, what is the probability? If the environment is known, I can build such a matrix. So it doesn't really matter which state I'm gonna get. I always know the probability of moving to the next corresponding states. I can put them in a matrix where each row would be summed to 1. So if I'm in a maze, I have all the information. I know all the probabilities of moving to all the directions, which would be one of the rows here. So if I know P, I know the environment. A reward RT is a reward function. It's the expectancy of the reward at next time step t plus 1, given the current state at time step t. So this is called the Markov reward process. You got state S, probability, state transition probability P, reward, and a discount factor called lambda. A lambda basically tells you it defines whether the reward would be myopic or far-sighted. So the return GT goal at time step t would be the immediate reward plus the discounted reward. At each later steps, he times the reward by a discount factor. If the lambda is 0, so all these additional terms would be 0, the return would be just immediate reward. So you're only looking at the short-term goal. You're not looking at long-term rewards. Whereas if you define lambda to 1, you're adding all the discounted future rewards. So you might be taking actions where it's not good for short-term reward, but it's good for long-term reward. So that's how he structured the goal. I hope it makes sense. I think in the lectures he also have several quizzes, testing how testing your understanding of using lambda. If you want to maximize only short-term reward, then you can just put lambda equal to 0. But if you really want to, considering all the future rewards to maximize the long-term goal, you better define a lambda into a value between 0 and 1. Again, value functions gives the long-term value of state S. It's defined the expectancy of the goal given the current state S. Again, the goal t as time step t is defined as the immediate reward plus all the discounted future rewards. So that's Markov reward process. It does not involve actions. And here in Markov decision process, because you're going to make decisions, you're going to take actions, he adds the finite set of actions, capital A, into the tuple. So again, S, P, R, lambda, and then with an addition of actions A, called a Markov decision process. So with Markov decision process, you can fully construct a problem, and using the Markov decision process, you can use all the later lectures, the ideas explained in later lectures, to solve a problem using the structures that you created. I know it's kind of boring, but I think these concepts are really important in order to build a good solid foundation to understand the later algorithms. Okay, policy it's called pi. It's a distribution over actions given state. So it's also a probability matrix. Instead of P, which is called a state transition probability matrix, it tells the probability from state S to S prime to the next state S prime. The policy pi is a distribution, is a probability of from state X to actions A. So it tells you the probability of moving to each of the next action. It tells you the probabilities of each of the next corresponding actions. So that's pi. So if we have a MDP in the policy, you will have a probability transitions probability the state transition matrix P. Yeah, so if you know P from S to S prime, you would also have a P S to S prime for policy pi, and that would be the summations of all the summations of all the P S S prime for each of the actions. You just times each of the P to its corresponding probability given what actions is you're going to take. And then you will have a reward under policy pi, which will be equal to the reward of each actions times the probability of each of those actions, and then sum it up. So basically just multiply. So basically you're at current state S, you times, and at current state S, there are several actions you can take, A1, A2, A3, and you have a probability of each of those actions, which is defined in pi. And basically you just times the probability of each actions and then sum them up. So the P as S prime A would become P as S prime pi, which is governed by the policy pi. And similar for the reward functions. State value function V pi and the action value function Q pi. V pi would be the goal given just the state. Q pi would be just the goal, would be the goal given both the state and the actions. So when you're calculating the reward, the goal. Again, the goal is defined as immediate reward plus all future rewards. You can simplify all the future rewards by replacing those future rewards with just the value functions of the next state. You can do some arithmetic rearrangement and replace the goal with just the immediate rewards plus the value function of the next state times the discount factor. Similar for the action value functions. And then the rest of the lectures, he explained Bellman equations and Bellman optimality equations, which is, if you look at all the future lectures, the algorithm he used basically are just derivatives or all iterations of this Bellman equation. So it's really important to understand what is Bellman equation. So I'm going to go back. And explain what is Bellman equation. Bellman expectation equation. So imagine you're at current state S, 0.3 probability of taking action A, 0.7 probability of taking another action. So the value function of the state value function under the policy pi at current state S would be equal to the action value functions times the corresponding probability, which is governed by pi, and then sum it up. It's basically like a tree. The parent node of the tree would be the summation of all its children nodes. So V pi would be equal to pi, the summation of pi times Q pi. I think that's easy to understand. And then if you're giving, wait, I think I'm missing a slide here. So basically, if I know the state, I have all the action value functions, I just sum it up. And on the contrary, if I have a action value function, so I have um, a, a, a dark dot here, at current, after taking this action, I might reach to different states. And then I'm just adding all the state value functions up to get the action value function. I think I miscopy paste this slide here, but this should be the this slide should be the calculation for the action value function. This should be a dark dot and then empty dot. But if I combine if I combine both of these slides, I'm gonna get this slide. So at time step s, in order to calculate the value function, state value function of current state s, I am gonna find out. I'm gonna have the next action value functions time its probabilities, and then sum it up. And then the action value functions would be, each of these action value functions would be the immediate reward it's gonna get plus the immediate reward, because I'm gonna reach to either one of the states here. After I take an action, I'm gonna get a reward, and then plus all the future states that I'm possibly gonna reach to, which is v pi s prime times its corresponding probability, which is defined in the probability transition matrix. Sum it up, then times a discounted factor. So that's how you're gonna. So that becomes the complete Bellman expectation equation for calculating the state value function Vs under policy pi. I hope it makes sense. Basically, just summing all the nodes in the tree in order to get the value function here for state S. Similarly, you can get the action value function Q pi by summing all the nodes in the tree. So for Q pi, you would, after taking this action, you're going to get immediate reward plus the state value each of the state value functions times its probability times lambda, and then so this would be the state value function, and then for each of the state value function, that would be just equal to the corresponding action value functions times the probability, which is pi, and then sum it up. So I hope it makes sense. At least it makes sense to me. Okay, so that's Bellman expectation equation. Bellman expectation equation. Why this is important? Because moving forward, if the environment is known, you need to find out which actions you're going to take, for example. So, which actions you're going to take. Imagine you're at current state. You want to know which actions to take. Then you need to calculate, okay, this action value functions here and the action value functions here in order to decide which actions you're going to take. Contrary, if after take it, you want to know, imagine there's another set of nodes here. You want to know you want to predict which action is better in the future. So you need to calculate the state value functions here and the state value functions here in order to decide which next state is better. So that's why we need to use this method to calculate the value functions of whether the states or the actions. And then to find out the best state or the best actions, you're gonna basically find out the max values of all these basically the max values of all these branches. So that is called a Bellman optimality equation. In order to find the best state, you're just gonna find the max action value functions. In order to find the best action value functions, you're just gonna find the best state value functions. Again, the action value function is equals the immediate reward plus the best state value function times its corresponding probability times its discounted factor. And then if you combine both of these slides, the best or the optimum state value functions would be the max of the action value functions, which equals to the immediate reward plus the best state value functions times the probabilities times the discount factor. And similarly, to find the optimum action value function Q star, you just need to get the best action value functions of the next state at the next state and at the next state and the action items after the next state. Okay, with that, I guess I'll take a pause to kind of summarize the concepts I explained in lecture 1. So I explained several terms, including state, S, state transition matrix, P, which defines the probability from S to S prime. I defined Markov reward process, which has no actions involved, and then Markov decision process, which has an actions involved. A policy called pi, which defines the probability from S to actions A. And then the policies and the reward for under a policy pi would be just the corresponding P and R times its times each of the actions probability, and then sum them up. We also defined two value functions called state value functions, given just a state, and a action value functions given both state and actions. The lectures talk about Bellman expectations equations and Bellman optimality equations, which is basically just finding the best value functions throughout the tree branches. And we're going to use this to find out what is the next actions to take, what are the to control a problem by finding out the best actions and by predicting the problem or planning the problem by finding out what are the best state value functions. So these are two different. One is predicting. I'm going to go back to lecture 1. One is predicting, evaluating the future, given a policy pi. What state is better moving into the future? The other is control. What is a better action that I'm going to take by comparing the Q of each of the by comparing the Q action value functions of each of the actions. I think this is one of the important concepts that I remember a few years ago when I was studying these materials. I don't quite understand why there is a V, why there is a Q, because the purpose of the problem is different. One is to predict, one is to evaluate the problem. The other is to control the problem. You need to decide what actions that you're going to take. Although by prediction you're going to have a implicit policy, meaning if you know which state you're going to get, you're going to find out what are the actions to lead to that state. But with control, with Q, you will be able to immediately find out which actions that is the best. So that's ideas and some concepts covered in lecture 1 and 2. I'm going to move to lecture 3, dynamic programming. I guess everyone knows what dynamic programming is. It's an iteration process of solving a big problem using the solutions of smaller problems, and then you iterate backward in order to find out the solutions. In this lecture, David explained using dynamic programming to using policy iteration and value iteration with the help of dynamic programming to find out the optimum solutions. So I'm going to explain what is policy iteration and value iterations. Okay, I guess I'll skip over to this slide first to explain what is policy iteration. I got quite confused when I first look at these slides. I don't know why it's doing like this. It's starting at v pi, and then why it's bouncing back and forth, and then it reached to the optimum state value functions. And this bouncing back and forth is a loop, which combines evaluation and an improvement. So when I was learning this, I got really confused, but I think I get a better idea now. So basically, imagine, I'm gonna make an analogy here. Imagine you're playing soccer, okay? You're shooting, okay? You wanna shoot the ball into the goal. At the beginning, you're probably not that good. Okay, the ball is not even moving into the goal. So how are you gonna improve yourself? You're gonna keep practicing, right? So this bouncing back and forth is basically practicing, or in deep learning, you're training. But again, this is not supervised learning. You're not using training data. You're just exploring and exploiting by yourself. Okay. So you're practicing shooting the ball. After you shoot a ball, okay, you take an actions, moving to a different state. You will evaluate yourself. Okay, I'm gonna shoot a little bit left to the left so that the ball can get into the gate. After a few rounds, so after you shoot the ball, you find out, okay, I should have moved to a little bit right, and then the next actions, the next cycles. So shoot the ball, improve, shoot the ball, improve. The next cycle is gonna shoot a little bit to the left, and then you're gonna improve it. So by iterating this process, I should shoot a little bit left. I should maybe shoot a little. I should maybe kick a little bit harder. I should have. I don't know. After several iterations, you finally are able to hit the ball into the goal. So that's policy iteration. You constantly. The loop has two parts. You're constantly evaluating the state value functions under policy pi, okay? And then from current state, moving to the next two states, which next state that I should move to. And then you generate a better policy from the previous policy. So here it's using a greedy policy. So basically I'm just comparing the next state value functions. I'm just using max function. It's called greedy policy to find out what is the next best policy. So policy iteration is just constantly, repeatedly doing this evaluation improvement cycles, and then it will be able to guarantee that it converge and it reach to the optimum optimum solutions, which he also gives a mathematical proof in the end, which is called contraction mapping, which explains that after this several iterations, it will reach to the optimum V star. So that's policy iterations. We also have, he also explained a value iteration concept, which is similar. Wait, where is my value iteration slide? Oh, right here. So value iteration, instead of policy iteration, it does not have value iteration online. There is no explicit policy. Okay. No explicit policy. Right, it's just updating the state value functions. Okay. I think I makes myself clear what is a policy iteration. I'm gonna go back to the previous slides to explain what each of the steps in policy iteration is doing here. So I'm gonna explain how it estimates v pi and how it generates this pi prime, which is better than prime. And then I will go back to these slides. So hopefully by then you will understand what is policy iteration. Okay, policy iteration. First part of policy iteration is policy evaluation. Problem is to evaluate a given policy. Okay, the solution is iterative application of Bellman expectation backup. Okay, at time step, so it's going to iterate from v1, v2 all the way to v pi. Okay, at each iteration for all state s, I'm gonna update vs from okay. So k here is the iteration steps. Vk. So I currently have vks. I have future states as prime. The goal here is to use future states as prime to update the value functions of the next iterations k plus 1, the state value functions of vs, not s prime, at the next iterations. So that's what it's saying here. We will use the future states as prime, the value functions of future states as prime at iterations k to update the current state value functions vs, but at the next iterations. So vk plus 1 s would be equal to the reward after the reward of each actions, the policies times its policies. So first he's calculating the action value functions here and then times the probability. So each of the action value function equals to the immediate reward plus discount factor times probability, state probability matrix times the state value function of at iteration k of the next state as prime. So yeah, so So he's just trying to calculate vk plus 1s using s prime of the previous iterations. So that's what it's saying here. Once he knows the once he knows vs at the next iterations k plus 1, he will compare. Okay, he will compare. Okay, where does he get this evaluate the policy? Oh yeah. So once he knows the value functions of the next state at the once he knows the let me once he knows the value functions of the current state at the next iterations k plus 1, he will compare improve the policy by acting greedily with respect to v pi. Okay, so he's evaluating the policies. He knows the state value functions of each of the states. And then he would be able to find out which actions that he's going to take, the optimum actions he's going to take by comparing the state value functions. So that's the greedy policy he was talking about here, by just acting greedy to find out the best actions by comparing the state value functions. Okay, I guess I'll skip, and maybe once I have better understandings, I'll come back to this slide and explain what it's trying to do here by acting greedily with respect to v pi. Improve the policy by acting greedily with respect to v pi. I think it's just comparing the v pi. Okay, so this is a generalized policy iteration where you evaluate v pi and then you generate a better policy by acting greedily. Instead of acting greedily, you can also do a so-called epsilon convergence of the value functions. So basically, instead of iterating all the way, you can define a stopping criteria. So it will stop after, let's say, k equals 3 iterations. It will just stop because that is sufficient to achieve an optimal functions, optimal policies. So that's called epsilon convergence. So with the concept with the explanation so far, he defined a generalized policy iterations. Basically, you're just repeatedly doing this evaluation and improvement cycles that will guarantee you to converge to the optimum. A value iteration is the same without an explicit policy. So it's just going to keep doing this, updating the value functions. But the immediate value function, it does not correspond to any policies. But how do we calculate the value functions? Because this is in a known environment, you know all the probabilities of state P, state transition P, and reward transition R. You can use dynamic programming. It's called full width backups. You use dynamic programming. You have all these nodes, numbers. You just use dynamic programming to effectively find out the value functions of the current state. But 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 once the problem scales up, the dimensions increase. DP will suffer Spellman's curse of dimensionality. You can't possibly calculate the value here. Use DP if it's if it has if the tree grows exponentially. There's just too many nodes to calculate, and it's very expensive to calculate. So that's the limitations. And then in later slides, he will use sampling. So instead of finding out, calculating all these branches, I'm just going to take one of the samples, and one of the samples will be sufficient to at least improve the value functions a little bit. But after several iterations, it proves that using just sampling, just taking one of these routes, it also helps to converge and find out the optimum solutions. In the end of the lectures, he talked about contraction mapping. I guess I will not go through the details, but I guess I'll basically just explain the ideas of contraction mapping. Imagine there's a piece of paper or a piece of cloth, and there's a fixed point on the cloth. Contraction mapping is basically like shrinking the paper or the cloth. It does not really matter which side, how much you shrink the cloth or the paper, but as long every iteration, you shrink a little bit. Every time, maybe this iteration you're shrinking on the left, the next iteration you're shrinking on the right. As long as you keep shrinking it, eventually you will get to the fixed point somewhere in the middle. So that's the idea of contraction mapping. It basically illustrates the thoughts here on the policy iteration. So it does not really matter how you improved it, how much you improved it, which direction you improved it. As long as you keep improving it, eventually you will reach to the goal. I think it's also a life lesson for me. It does not really matter, like, you get an A or A minus in an exam. As long as you're better than your last exam, you're improving yourself. I mean, it just takes maybe more iterations, but in the end, you will understand it. You will reach to the optimum. You will converge. So that's a contraction mapping theorem. The last slide he gives, which I copy paste, explains the idea of sample backups. So that I think I briefly explained as well. In this lecture, we use dynamic programming. We know all the tree nodes, but it's impossible because of curse of dimensionality. So in future slides, he said here, in subsequent lectures, we'll only consider sample backups. So I'm just gonna sample one of the routes, one of the tree nodes, and then use that to learn the problem. The advantages would be it's model free. I do not need to know everything about the model. No advanced knowledge of MDP required. I do not need to know the P, the state transition probability matrix. I do not need to know the probability of R. After taking each actions, what are the probabilities of each actions? And it breaks the curse of dimensionality through sampling. I'm just going to take one of the samples. the cost of backup is constant, independent of the number of states. So because I'm only taking one of the actions, one of the routes, the backup is constant. I just need to add everything. I just need to add everything up. So that's lecture 3, dynamic programming and the idea of policy and value iterations. All right, moving on to lecture 4, where he talks about Monte Carlo learning and TD learning. This is a slide from previous lectures illustrating the generalized policy iterations, where you continue this cycles to improve the policies. A Monte Carlo policy evaluation. Okay, so you're giving a you want to learn VPy from episode of experience under policy pi. Okay, so you have a series of these state S1, A1, R2, and then S2, A2, R3, all the way to SK. And then recall this is how calculate the goal. Recall this is how calculate the VPy S. Monte Carlo policy evaluates use empirical mean term instead of the expected term. So Monte Carlo is basically just sampling one of the routes here, and then update VS at time step t by adding the difference between the goal and the current and the VS at time step t times a step function times alpha, which is the learning rate or a step rate. So he's going to update VS a little bit in the directions of the difference of the goal and VS. So that's Monte Carlo backup. He's at time step t, state S, he's going to sample one of the tree branches. He's going to follow these nodes all the way to a terminal. Whereas TD, temporal difference, TD is just taking one of the steps. He's just taking one more steps. So instead of reaching all the way to the terminal, TD is just making one steps here and then update the value functions. So yeah, he's comparing MC and TD. MC would be updating value function towards the actual return, GT. GT is the immediate reward plus all future rewards all the way to terminal T. And then TD0, which is taking one more steps, is by updating VS towards, so he's replacing GT here with immediate reward plus discount lambda times the value function of the next state. And this is called a TD target. So he's replacing the TD target with GT because sometimes it's impossible to always reach to the terminal state. So taking one more step is more effective. And I think he talks about bias and, oh yeah, he has one slide here. He talks about bias and variance of TC and of MC and TD. MC has more variances, but no bias. TD has more variances. Anyway, back to this slide. This is called TD target. The delta T, which is TD target minus VS, is called TD error. So that's how it is updating the value function at time step t using Monte Carlo and temporal difference. Again, temporal difference is just taking one more steps instead of reaching all the way to the terminal. Bootstrapping, MC does not bootstrap because it's reaching all the way to the terminal. Uh, Dynamic programming bootstraps, TD bootstraps, sampling, all of them samples except dynamic programming because it's covering all these tree branches here. Again, it's just another chart illustrating these ideas. The DP, you do full backups. It knows all these nodes, and then he backs up to calculate the value functions. Temporal difference and Monte Carlo are sample backs up. It just take one of the branches. But temporal difference bootstraps, it just take one more steps. Also called as shallow backups. Compared to Monte Carlo, it do deep backups. It takes multiple steps and reach to the terminal state. Here he explains TD lambda. So instead of taking one step, TD0, what if we can take steps somewhere in the middle, and then use that to update my value functions. And then what if I can do multiple such updates and then combine them? So that's TD lambda. So here it's taking 1 steps, 2 steps, 3 steps, all the way to lambda steps. I can find out the TD target of each of these steps and then add a weighted factor 1 minus lambda times lambda squared if I'm taking 2 more steps, or lambda times capital T minus 1 if I'm taking multiple steps. I can just sum all of these up. I can just times this weight factor and then sum them up. So this is called a forward view TD lambda. I'm replacing the goal GT here with GT lambda, which equals to the GTN, and is the number of steps I'm going to look forward, times a weighted factor. So forward view TD lambda would be to update the value function towards the lambda return. It looks into the future to compute GT lambda. If lambda equals to, or like MC, it can only be computed from complete episodes. Yeah, because I need to I need to keep moving in one of the episodes. I need to keep moving until to the terminal states. This is called forward view TD lambda. Instead of looking forward, I can also look backward. So a backward view TD lambda would be to update this TD error with a so-called eligibility traces, ET. Eligibility traces is defined as frequency heuristic and recency heuristic. So imagine so every time, so if I, how do I explain it? Every time I reach to a state, I'm gonna add one more up. So this is what this chart is showing here. Every time I visit, I add one more. But if I do not visit, I gradually decay it. So that's what this function is doing here. Every time I visit state S, I add one more. But if I'm not visiting state S, I'm discounting it by adding a discount factor times a lambda times the previous the eligibility traces of the previous time step t minus 1. So if I visit more, I will keep adding more. But if I do not, but I'm not visiting any, but I'm not visiting state S more, I will slowly decay. That's what is so called eligibility traces. So here I'm updating VS and replacing the goal with the TD error and the TD error and the T with the T with the eligibility traces. The TD error is still calculated as this function over here. So basically, I'm looking back into the future to find out to update my value function. This previously I'm looking forward, and now I'm looking backward. Looking forward, you need to compute from a complete episode. So you have to update once you finish the episode. It's also called offline learning. Whereas a backward view TD lambda, you're looking back into the future. Every time you make a move, you can update it by looking past, by looking back, by calculating the eligibility traces. If I visit more of this state, then I'm gonna update more towards this state, because eligibility traces at time step t of s is bigger. That's called online learning. So looking forward, I cannot update online. I have to update VS offline. This is called offline learning. And then backward view TD lambda, I do not need to look into the future. I can update immediately. This is called online learning. I can learn as I go. Again, it's just comparing just comparing TD lambda and TD zero. If lambda equals 0, only current state is updated. This is exactly equivalent to TD0 update. Summary of forward and backward TD lambda. If I'm looking forward, which is an offline update learning, if lambda equals 0, backward view and forward view is the same. Yeah, I guess I'm still confused about this slide. I guess I'll skip, but I think I explained the concepts of offline learning and online learning. Also the ideas of forward view and backward view. So that's Monte Carlo and temporal difference. And then lecture 5 talks about controls using Monte Carlo and temporal difference. Last lecture, model-free prediction. We only estimate the value function of an unknown MDP. So everything is about the state value function. Now in this lecture, we will optimize, we'll do model-free control, we'll optimize the action value function. Here it talks about on-policy and off-policy learning. On-policy means learn on the job. Learn about the policy pi from experience sampled from pi. I want to learn soccer. I'm just going to play soccer until I learn it. Off policy learning, look over someone's shoulder, learn a policy from an experience sampled from you. So instead of practicing soccer, I am watching soccer movie. I'm watching soccer games on the TV. I'm just watching, observing, and then practicing. Use that experience that I gained from the soccer games to improve my current policy pie. That's called off policy learning. There's several benefits of off policy learning because you can sample your previous experiences. You can you can you can use a different training sets to train the current policy. So Monte Carlo policy iteration. Okay, remember a generalized policy iteration. You do a policy evaluation, and then you do a policy improvement. A Monte Carlo policy iteration would be just replacing the how you update the value functions with Monte Carlo policy evaluation. You're updating Q pi with Monte Carlo evaluations, and then do an epsilon greedy. Epsilon greedy would be just slowly, instead of max, to do a max, you do a epsilon greedy max at probability of epsilon. You do max at probability of 1 minus epsilon. You do random selections, and the benefit is you're adding a bit of randomness into the equation so that it gets a better chance of finding the local or global or local optimum. I see a lot of algorithms include such randomness. For example, you don't want to pick a very big learning rate in machine learning because you want to fully explore the path. In machine learning, you're also augmenting the training data to include a bit of randomness. The more randomness you include, the model becomes more generalized. In other words, you will not be able to overfit the model. So that's what epsilon greedy is. Monte Carlo control, because you're so because you're sampling the queue, you do not know the environment. It's model free learning, so every time you evaluate it's remember the graphs that explains full backup and sample backs up. Because we're doing sampling, we're not using DP to do a full backup, and that's why these lines are not going all the way down and all the way to the top and all the way down, because we're only sampling. But because of contraction mapping theorem, even though we're sampling, we're still able to reach to the optimum. That's what this slide is trying to explain here. So for Monte Carlo control, you're updating the Q functions by using Monte Carlo sampling. So Q would be approximate to Q pi. And then for policy improvement, you still use epsilon greedy policy improvement. So this is for Monte Carlo control. For a TD control, you're just replacing this Q pi with the TD learning. You use TD learning to update the Q instead of Monte Carlo. So there are several pros and cons of using MC or TD. TD has lower variance. Monte Carlo has more variances because every time you're sampling, every time you take a steps, there is a variance. But for Monte Carlo, you're taking multiple steps all the way to the terminal. Every step has a variance, and you you multiply all these variances all together, which will create more variances. That's why Monte Carlo has higher variances. Unlike TD is only taking one steps or fewer steps, so it has lower variances, but it has more biases. So there's a trade-off of using MC or TD. The on policy, you're learning on the go. The on policy TD learning is also called a SASA, because you're updating the action value function Q SA by the next action value functions Q S A prime, Q S prime A prime. So SAR S prime A prime. It's also called SASA. Again, the action value function SA would be updated by after state S prime and taking actions A prime, you're updating the Q with the TD target. R plus lambda times Q S prime A prime times the learning rate alpha. So the on-policy control with SASA, similar to on-policy control with Monte Carlo, would be just replacing this Q with QPi, and QPi is calculated using SASA. So this is the SASA algorithm for on-policy control. We're gonna use epsilon greedy. We're gonna choose an action from the policy derived from Q. So we're gonna either choose A from S using policy derived from Q. Because there's no policy involved, we're going to derive the actions from Q. I'm going to take an actions right over here. We'll receive a reward, observe reward, and then observe the next state S prime. And then we'll choose the next actions from S prime using the policy derived from Q. Again, it's epsilon greedy policy. Then we'll use Q S prime A prime to update Q S A. And then S prime would become the next S, A prime would become the next A, until S is the terminal. That's SASA. It's on policy control algorithm. The derivatives of SASA would be a forward view SASA and a backward view SASA. Simply saying, you're just basically replacing the goal with a forward view SASA Q and a backward SASA. You're just basically replacing the Bellman equations with its corresponding target functions. So for forward view, it's going to be QT lambda. For backward view SASA, it's going to be the TD error times the eligibility traces, which I explained earlier. So a complete SASA algorithm would be, you take an action, observe R, S prime, you choose the next actions, A prime from S prime. These are all the same from the previous SASA. And then for a backward view, you're also going to calculate the eligibility traces here. Then you use the eligibility traces to update Q, and then you're going to update the eligibility traces with alpha and with lambda, and with a discount factor. So that's a backward view of SASA. It's an online algorithm to update the Q functions. Model free as well. So far we talked about on-policy learning. The lecture continues to talk about off-policy learning, basically using a behavioral policy mu to update the current policy pi. Why this is important? You can learn from observing humans. So like I mentioned earlier, you can watch a soccer games in order to learn how to soccer. You can reuse experience generated from episodes. So you're practicing in the soccer field. You can also use your previous experiences to help you learn about optimum policy while following exploratory policies. So this is the randomness concept I was talking about earlier. Why the more you explore, the more chances of getting to an optimum path. So this is what it's saying here. You can learn by following exploratory policies. You learn random, but eventually it helps you to get to optimum policies. To do off policy learning, you have a target policy pi and a behavioral policy mu. So to learn from behavioral policy to update policy, you need to do a so-called importance sampling. So basically, it just basically just times the ratios of the two policies to up to. So here you're updating a distributions from P, but what if you want to update P with the different distributions Q? So you just need to times a ratios between P and Q. So how are we going to update? So with importance this. So with the concept of importance sampling, how are we going to update off policy Monte Carlo using the two different policies, mu and pi? Well, at each time step, you're just going to times the ratios of the two different policies to update GT to update GT at policy pi using a behavioral policy mu. You're just gonna update GT times pi divided by mu at time step t times the ratio of the next time steps, the ratio times the ratio of the next time steps, all the way to the terminal time steps. So it's basically just times a ratio of these two probabilities, and use that goal to replace the TD target. As you can see here, because it's timing the ratios at all the time steps, each time step will have a variance, and you times these variances all the way up to the terminal. So off policy Monte Carlo will have a very, very big variances. So in practice, I think it's not used very often. In practice, we use off policy TD learning, where you're just updating one more steps or a few more steps, also by importance sampling, so that it will have a much lower variances. In practice, we use the lecture talks about Q learning. Q is the state action value functions, because it does not need importance sampling. Yeah, it does not require importance sampling. The algorithm works as follows. Next action is chosen using the behavioral policy, which is mu. Okay, we're gonna, given the current state, we're gonna sample from the behavior policy. At current state, given the current behavior policy, I'm just gonna take a random next actions, a t minus 1, t plus 1. But we will consider alternative success actions a prime to update the action value functions. So, okay, so again, all these algorithms are playing around with the with the TD target here. So for offline Q learning, the actions to take is sampled from the behavior policy mu. So after I take this random actions from mu, I will use my successor action A prime to update my Q. So A prime is still taken from the target policy pi. As you can see here, I'm still using A prime, which is sampled from pi to update the Q. But the actions that I'm going to take is actually from a behavior policy. So it's like I'm going to take soccer as an example again. So I'm practicing soccer in the field. The next actions I'm gonna pick is gonna be randomly sampled from one of the soccer games that I saw on the TV. It does not come from my current target policy pi. It's from a TV. It's from a games that I watched earlier. So after I take these actions, I will observe what would be my I will observe what would be my following action states, and then from those states, I'm gonna pick the successor actions A prime derived from my target policy pi, and then I'll use that to update my Q values. So I'm updating my target policy, my Q values from a experience that is outside of my target policy. That's what basically Q learning is. Well, I hope it makes sense. I hope I explained well, but I guess I'll move forward. Off policy control with Q learning. So here it's just it's saying instead of greedy policy, you can also do so the target policy is updated via greedy respect to the Q functions. Behavior policy is epsilon greedy because you want to add some randomness. And then Q learning target simplifies to immediate reward. So target TD target immediate reward plus the max, because it's greedy respect to Q. It max of the Q values of the next states and actions. Yep. Q learning is also called SASA max because we're taking a max of the next time step, next actions of the Q value functions. So that's why it's also called the Q SASA max. It's updating the current Q values by using the max Q values of future state and actions. Oh, this is a slide from lecture 2, which is a Bellman optimality equation for Q star. If you compare the two, the Q learning control and the Bellman optimality equation for Q, they look pretty much the same. The target is a reward plus discount factor times the max of the future Q. Well, here, because it's a known environment, it's also times a probability. But here, since we're sampling, we're just using the max here. This is the official algorithm for Q learning off policy control. Again, you're choosing A, epsilon greedily choosing A, randomly choosing A from the behavior policy, and then you're updating the Q with using the target policy. Okay, two summary slides to summarize what we've learned so far. With the environment known, you know everything about the environment, the probabilities. You can do full backup using dynamic programming, and then you can update the state values, the action values, and then find out the optimalities. But with the environment unknown, the model is model-free learning. We can only sample one of the tree branches. You have a TD learning to update the state value functions, SASA to update the action value functions, Q, and then SASA max to find out the optimum state action value functions. And then all these updates are simply just replacing the goal here. With TD learning, you're replacing the goal with this function here. With SASA, you're replacing the goal with these functions here. It depends on its forward view or backward view. With backward view, you're just adding an additional eligibility traces term. And then for Q learning, you're updating the goal with the max of the future states and actions. So that summarized everything I've learned from lecture 1 to lecture 5. From the basics, from the ideas of reinforcement learning, what it's trying to do, to how to structure using Markov decision, how to structure the problem using Markov decision process, to using dynamic programming in a known environment to iteratively solve the problem using policy iteration and value iterations, where policy iterations, you iteratively calculate the value functions and also use that to derive the policy, update the policies. Comparing to value iterations, you just keep iteratively updating the value functions without updating the policies, but the policies can be derived, can be derived from the values. To Monte Carlo and TD learning, to sample, to do sampling in order to update the value functions. And then here, in the last lecture 5, we learned how to do how to use TD and how to use MC and TD to update the Q value functions to do controls. We also talked about on policy and off policy learning, using experiences from other policies to update the target policies. So I hope my explanations is clear and precise. I think I also gave several examples trying to make some analogies and making analogies to explain the ideas. It's probably very boring to listen to till this point, but I hope you learned something new. Moving forward, I'm going to talk about lecture 6 all the way to 10. I guess I'll skip 9 and 10 because there's a lot of mathematical equations that I'm still trying to figure out. But from lecture 6, we're just basically scaling things up using neural networks because, like I mentioned, you cannot fit everything into a matrix of V and Q. Once the number of states or number of actions, the dimensions of actions and states goes up. So in lecture 6, it talks about using neural networks to update the value functions using incremental methods, stochastic gradient descent, or batch methods least square, with no policy involved. The policy is derived. And then lecture 7 will talk about parameterize the policy directly and update the policy directly using neural networks. And then you can also combine both V and Q, both of these two neural networks together to become an actor gradient policy, to become an actor critic policy gradient. I think this here it talks about a vanilla version of the policy gradient algorithms. I guess moving forward, I will stop at lecture 7, and then I'll briefly talk about the rest of the lectures to close out this video. So lecture 6, first it talks about the problem with large MDP. There are too many states and actions to store in the memory. It's too slow. So the solution is to estimate the value function with function approximations. And it also helps to generalize from seen states to unseen states. Again, we update the parameters using Monte Carlo, using MC or TD. So here we're estimating V pi s with a approximated function V s with parameter W. The weights. There are several ways to define W. You can give input S with parameterized S with parameters W. You give out approximated V, or you can approximate Q, or with just, so here you're approximating Q with input S, both S and A. You can also parameterize Q with just the input of S. The most naive way to update this would be to using a differentiable function such as neural network. It's differentiable. You use the gradient descent to update it. So the following lectures explained incremental methods to using a stochastic gradient and a batch method. You're just taking the least squares of all the batches. Here it briefly talks about what is gradient descent, basically updating towards in the direction of the gradient. So here it's calculating the partial derivatives of respecting to all the weights in order to find the local minimum of the loss function. You're just updating in the direction of respect to the gradient. Here is just another slides to explain how we use stochastic SGD to sample the gradient and update the weight. So delta W would be equals to the learning rate times the gradient of the weight would be equal to the difference between V and Vs minus the parameterized V times the gradient of V. So basically we're just using a chain rule. The gradient of JW of W would be to 2 over here, and then times this times the derivative of this. So here it's using a feature vector to represent a state X. And this feature vector would be equal to the states times a weight. And then the gradient of the weight would be simply put as the learning rate step size times the errors times the feature values.